Okay, welcome everyone. So today is my pleasure to introduce Xingda Wei from iPads, and we have a lot of attendance from China, from Singapore, from Edinburgh, from Zurich. So it's great to have you all here. Let's listen to this very interesting talk that I had a chance to watch at a workshop before. It's also it is a published work as far as I remember, and yeah, it's very interesting way of looking at system and abstractions in the serverless context. And yeah, let's try to be interactive and ask questions and engage in discussion. So Xingda, please go ahead.
Okay, so I'll begin. So thank you, Professor Dimitri, for the invitation and the introduction. So today I'm very happy and honored to present our recent thinkings and our build systems for serverless computing. So let me start with a brief introduction of how we start this kind of research. So to see why we need to accelerate serverless computing, let's see how it is evolved from the beginning. So before serverless, if an application wants to deploy an applications on the cloud, like deploy a server to handle the user request, they have to provision a program on server, which typically means they need to rent a virtual machine on the cloud platform. So if the machine is deployed, then upon the request coming, the cloud provider will direct the request to the provision program and process it. So key questions for the developer is how many programs need to be provisioned on the cloud. So ideally, we want the number of deployed programs to be the same as the requirement of the workloads. So if the deployed resources is less than the workload requirement, the user request may face latency increases and causes angry users. So suppose in a left corner figure, we can see an example that if we only deploy one server program and it can only process one request per second, and if there is a concurrent request, say request 2 come concurrently, so it will be blocked due to the insufficient computing resources, and only if the first request has been processed, that the request can be served. So okay, so how to cope with these kind of scenarios? So traditionally, the developers need to manually scale the resources to handle requests. Actually, even nowadays, many popular services like ChatGPT also adopt such a strategy. For example, the right screenshot is one day when I was using it, it tell me that ChatGPT is experiencing a high workloads and they need to manually scale the system. What does manually scale the system mean? Typically in traditional serverless computing, we need to deploy one more servers on a spare virtual machine or a cluster, and such that the requests can be processed concurrently. However, it is actually very challenging to predict the number of servers required to run all the requests. For example, in the middle figure, I plot a real-world serverless traces from Microsoft Azure. You can see that the request changes over time. So if we deploy resources according to the peak usage, which is the common case, that many server resources will be wasted, and the user will pay extra money for the unused resources. For example, in the right figure, if there's only one request for the overall system, the server one will be wasted. So serverless computing actually takes one step forward and aims at liberating developers from provision server programs. But the server is still here because we still need some server to handle the request. The key insight is that we do not need users to provision servers. They only need to register mapping and tell the platform like which server program is capable of handling a user request. And upon a request coming, the platform will automatically find the server program that can handle this request and launch some computing resources such as virtual machine, micro virtual machine, or containers to process them. And upon the computation has finished, the platform will also clean up the resources such that the overall resource utilizations will be improved, and the user don't pay for time that they do not occupy cloud resources. So as we can see in our previous example, if we have a workload that changes over time, for the low workloads that in serverless paradigm, we do not need to deploy any server programs. And if there's some request burst that we need multiple large computation power to handle it, in serverless paradigm, we can directly spawn multiple containers for it. However, although serverless make the developers for one step forward, it actually adds many costs to the existing application running. Actually, our profile have shown that in a serverless running time, in using serverless paradigm to handle requests, it could actually incur 50 more times performance overhead. And from the figure we can clearly see that in a serverless paradigm, the middle figure, it has the additional cost of like a resource provisioning, and it has the cost of setting up a network connection and so far. So why is as current systems for supporting serverless has such a large overhead? So in my opinion, I think it is because that serverless is only a paradigm. And the system we use to support this paradigm is built from existing abstractions like container and like the C group and namespace that the operating system provide. However, these abstractions are not designed for serverless. So one important case is that the container abstractions has greatly simplified the application development and deployment. However, the container is originally designed for running microservices, which is a long-running services that does not care about the resource provision, dynamic resource provision over time. So optimizing its performance actually is clearly not the main goal of the original container. But if we want to use containers to support like serverless paradigm, we have to pay for the additional cost for it. So how to address this kind of performance overhead? One possible solution is like we can provide some new abstractions from scratch. For example, there has been many studies in the both academia and the industry that we can use some new sandbox environment like WASM, which is lightweight in startup and it can run handle requests. Also, Mock actually does not even use a sandbox like container at all. They run different requests in the same runtime in RPCs for better performance. So the benefit is clear that with the new abstraction like WASM, it is designed for lightweight startup, we can hide or eliminate the container startup cost. But the drawbacks is very clear. For example, in WASM, we have actually me and our students have been playing with WASM for some time, and we find it is very hard to use WASM to support some not so hard program. Like if you want to run a PyTorch in a Python, currently it is not supported in the WASM runtime. And it is not so hard to support, but we still need many engineering efforts such that most current applications cannot benefit from it. So and on the other hand, if we do not use container at all, we just lose the isolation that container brings, which is very essential to serverless actually, because serverless applications that run on the cloud, which is a multi-tenant environment. So how do we tackle this problem? So our my main goal is that we need to preserve the existing container, actually like the existing abstraction, for example, container, which is close to support serverless applications. But instead, we want to propose some new abstractions at the operating system level, which means that we use this kind of operating system abstractions to accelerate the container startup and stuff. So by doing so, a major benefit is that we can transparently support existing applications that is running on the container. So in the remaining of this talk, I will mainly talk about our first work that we propose remote fork abstractions to accelerate the container startup for serverless computing. So as you can see, that container startup is actually famously slow. For example, if I run the right half of the figure, which is a Python program, and simply execute some input and print hello world. So if I run it with a container like Docker and compare it with running on a bare metal machine, I would find like you could find like a 9,000 times slower doing for this program's execution. So our operating system abstraction mitosis actually can start container very fast. It can start a clean container. It can start such a container from at a clean machine within 5 milliseconds, and it can start 10,000 such containers on 5 clean machines within 1 second. So for clean machine, I mean that the container has the machine has not executed anything related to this container before. So how can we accelerate container startup without proposing some new container abstractions? So I will first show, I think we need first to characterize how why container startup so slow, and why existing operating system primitives cannot support efficiently supported container startup. So suppose that a user want to start a container like by typing this command docker run on container to start a container. So the first step the Docker runtime do is that it will download image from Docker Hub. And afterwards, it will use some existing operating system abstractions like C group and namespace to set up the isolation environment for this container, which basically limits the resource usage of this container and isolate it from other containers. And finally, since serverless programs are typically written in a high-level programming language like Python or Java, so we need to initialize the runtime for these languages, such as we need for Python, we need to initialize the language runtime and import the libraries the program needs. After all these steps have finished, the containers can really run the application code. So many work has been being proposed to reduce all this kind of cost, but the most straightforward one is like we can optimize download image with some fast networking. But even we have the fast network downloading images from a Docker Hub is still very costly, and we can not eliminate it. So for the containerization problem, there is some great work SOC proposed in using ATC 2018. It actually uses a technique called pooling to reduce the operating system's overhead to set up C group and namespace. Actually, it is very effective. In our experiment, we find that it can completely eliminate the containerization cost. But the remaining stuff to deal with, which is very hard, is how to quickly initialize the runtime, because we cannot redesign the language runtime for the serverless computing. So our key observation, actually, this is also made by many existing work, is that container initialization is actually a process to transform a process memory state to another memory state. So let's use Python runtime initialization as an example. In Python, when the runtime initialized, it will do the three following things. First, it will load downloaded modules to the memory. Second, it will translate the downloaded modules to the Python bytecode that can run by the Python virtual machine. And finally, it will execute some module, some initialized routines in the module, for example, in the PyTorch. So all these steps can be seen as translate the virtual memory of the running process from a state to another state. So the idea is that if we have an initialized state of a container, and if another container start, if we can reuse the in-memory state of another initialized container, then we can totally skip the image download process and the runtime initialization process, and it is extremely fast. But the question is that for serverless computing, how efficient can we implement this inherit? So we find that this inherit means that basically has two requirements, and we has one requirement besides the fast performance, and we call it no promotion concurrency. What does no promotion concurrency mean? So it means, so suppose that we want to start n containers on a cluster of machines. So the promotion concurrency means that the number of required initialized state that needs to accelerate the container startup of these containers. And we believe the ideal case for developer is that we need no promotion concurrency, which means that which means that we only need O1 the pre-deployed state of these machines. So this completely eliminate developers from deciding how many instances will be optimal for accelerating serverless functions. So using this kind of no promotion concurrency requirement, we use it as a lens to examine how existing abstractions can provide so. So we find that many existing solutions cannot provide no promotion concurrency, or it provides so with a huge performance cost. So the first abstraction, maybe it is the most widely used, is the caching technique. So in a caching technique, when a container that runs a program finishes, it will call a Docker post command to store its in-memory state it will freeze its state in the OS, so that if a later function request comes, we can use Docker npost to start the incoming request directly from the existing post instances. So this kind of post and npost is implemented by the operating system, and it's extremely efficient. For example, we can measure that it can npost container like in 1 millisecond, which basically has nearly no overhead. But the problem is caching is that the number of cache instances must match the number of requests. For example, suppose I have a second request to come, and if I have no such cache instance for it to use, I have to start a container from scratch. So basically, in a caching techniques, we need ON containers promotion to cope with the incoming request. And since N is unknown, we cannot very accurately decide N. So it is not optimal for the developer, since we have to fall back to the original server for computing, that we must decide how many instances we must use for the better performance. So another abstraction that proposed in existing literature is the fork primitive. Basically, fork I think is an improvement over the cache strategy, which means that once a container has finished the execution, so we'll also freeze its memory in the operating system. But once a request comes, we'll not impose it, but instead we'll use the operating system's fork system call to create new containers on the fly. So basically, fork has achieved no promotion concurrency on a single machine, because on a single machine, we can use one parent instance to start any subsequent child request. But fork has a significant drawback, is that it cannot scale to multiple machines. But this is that if we have many requests that we cannot fully deploy all these function instances on one machine, we have to deploy it on n machines. And in such cases, we need to decide the number of machines we need to deploy the parent instances. So this as you can see that the number of resource provision is also not constant. And you can see it's even challenging for developers to decide the number of fork instances, because the number of machines used not only depends on the number of requests, but also depends on the available resources on the platform. So can we make one step further? So our observation is that fork is a great primitive on a single machine which achieves no promotion concurrency. So can we make a step further, that we extend fork abstraction to a remote fork abstraction, so that we can start any container on a clean machine by forking an existing parent container at some node in our cluster. So for example, suppose I have a machine at this IP address and finish the initialization. And we can add some Docker command to freeze it in the memory. And afterwards, we can use Docker fork. We add a new command, Docker fork, to start some this image on that machine. And our system can transform the pre-initial state from that machine to the started machine and run the application code. So this can actually completely achieve no promotion concurrency even on a cluster of machines. So the remaining question is that how can we implement remote fork efficiently? So actually the standard mechanism to implement remote fork, actually also introduced in the vHive, is that we can use a technique called checkpoint and restore. So in the checkpoint phase, suppose we want to fork a container from a parent machine to a child machine. So first, we will checkpoint the in-memory state of this container to the core machine, and we will dump it into a file. Afterwards, we will transform this file into a distributed file system or cloud storage, so that later child can find it. So upon a transfer, upon a client started, it will read the file from distributed storage and restore the in-memory state from this file and continues running. So is this kind of strategy efficient enough for remote fork? So we do an experiment based on CRU. It is the state-of-the-art checkpoint and restore technique for containers, and we have also optimized it with a fast file system, which is backed by RDMA, and also we stored file in memory. But we can still see that the overall end-to-end latency of a remote fork based of checkpoint restore based remote fork is slow compared to the cold start, especially when there are many states we need to transfer from one machine to another machine. So we attribute this to two key reasons. First is that to start a remote fork, we need to checkpoint the entire process to a file, which is costly. And second, transferring reading the file from a segment storage and transferring it to the local machine actually is also very costly, because the cloud storage is not optimized for the remote fork scenario. For example, suppose that like we have a fork, or we will have a child server that as child container want to read a page at the parent. In the traditional networking solutions, we need to it will translate into a TCP/IP call, and will send an RPC to the parent server and read it from the memory, and finally return back to the child. So this process actually is very, very costly, especially the CPU cycles wasted for the network processing and memory copies. And even we do not consider the storage overhead of a distributed file system. So can we make it much faster? So our key observation is that the data centers has been deploying a new networking feature, namely RDMA, which allows a child CPU to directly read the parent's memory without any CPU involvement, and it can be extremely efficient by achieving the close to hardware's limit. For example, suppose now we have a child that wants to read a page at a kind of address. So with RDMA, we can directly use the hardware accelerated feature of it to directly transfer the parent's memory to the local memory without any parent CPU involvement and without any memory copy. So with this powerful networking feature, our observation that we can actually implement remote fork by imitate local fork with RDMA. Namely, we read the remote memory of the parent container step by step. So let me more specific about this. So suppose I have a parent machine and a child machine, and the child machine wants to fork a container from the parent. So at the first, we do not need to dump the memory into a file, because the child can directly use it with RDMA. So with the parent only needs to mark the parent's page table as copy on write, such that the later network reads will be isolated from the concurrent parent execution. So now suppose that the child wants to fork a container from the parent. It will send an RPC to the server to read the page table of the parent container, similar to local fork. And afterwards, if a child touches a pages that has been not been fetched by parent, it will find the address from the read page table and use one RDMA to read it from the parent. And this is extremely efficient, because it bypasses CPU and bypasses the storage stack. So with the RDMA business solution, we proposed a system called mitosis, and we can see that mitosis completely eliminated the aforementioned overheads, including checkpoint container and transferring the file from the distributed file system. And actually, it can be no slower than the vanilla cold start. So in conclusion, when compared to the state-of-art solutions, we can see that existing solutions like warm start or eliminate caching or fork either do not achieve no proportion concurrency in a distributed settings, or they cannot have cannot have a better performance than mitosis. So to conclude that, we can see a real evaluation of applying mitosis to a serverless platform. So in this experiment, we emulated the workload traces from Azure, which is changes over time. So our baseline is FN, an open source project, because when we done this project, the FN is a standard platform to do so. So FN adopts the caching solutions we described before to cope with the slow container startup problem. So basically, after a request finishes, FN will cache a container for like 30 seconds to serve future requests. So we can see that with time increase, the memory usage of FN actually is much larger than the request handling, because we need to store the cache instances. But for mitosis, we only need to store one instance all through the cluster. So our memory usage actually is trivial, and it is independent of the number of invocations. So we can see that the overall memory usage of mitosis is all orders of magnitude higher than the caching-based solutions. And more importantly, it can also achieve a better tail latency, because we can completely eliminate the container startup problem. But in caching-based solutions, when there's a cache misses, it has to fall back to the traditional method to doing so. So in conclusion, in this talk, I present our abstraction called remote fork. We believe it is a powerful operating system abstractions for accelerating container startup. And actually, when we developed remote fork, we find it is much powerful than we think. For example, besides accelerating container startup, it can also support serialization and deserialization-free state transfer between serverless functions in a serverless workflow. And there's also many challenges and techniques and optimizations we make these things work, such as how to manage distributed memory with RDMA, and how we optimize the performance of remote fork with prefetch and caching. And our code is also open source. If you have interest, please check our paper and code. So finally, due to time limits, I will have a final conclusion and some outlooking to my today's talk. So in the main theme of my talk is that I want to show an operating system abstractions can accelerate many parts of the service computing, like container startup. And I think operating system is a good place for acceleration, because it can brings transparent acceleration to the above running applications. And I believe there's many more room to the top. For example, we have a recent work which called distributed merge, and it uses an operating system based distributed shared memory, which can eliminate all the serialization and deserialization costs in service workflows. And we have also some works on reducing the network connection time for service function. And I think there are some future workload which is more interesting, like like AI. So in like you using model inference. If you execute AI inference in a service platform, you also faces the container startup problem. And the existing checkpoint technology cannot very efficiently support GPU. And I'm also working on projects to accelerate a cold start of a container that involves GPU or XPU for AI workload. So finally, I have some remarks and some credits with the vHive community. So in my personal thoughts, maybe wrong. If I'm wrong, please point out. So in my limited understanding, I believe vHive actually has two parts. The first part, when I first know it, I saw this was a wonderful techniques proposed in many research papers. Like in your AskPros paper, you propose some prefetching mechanisms for the checkpoint and restore. And second, I found it is very great platform based on service computing. And actually, in my current research, we actually used some techniques proposed by you guys. For example, we currently has adopt mitosis to micro VM setting like firecracker, and we find that prefetching is much important in micro VM than container, because container page fault is much slower much slower than container. So actually, we have adopted your proposed prefetch mechanism in vHive in our micro VM based remote fork, and we find actually it's very good. We have find no performance actually improvements. So basically, this is one place that I adopt. And the second I found recently, the vHive also supports workflow execution on Knative, which I believe this is actually a very great feature, because we start a project like last year and we're trying to run workflow on Knative. And I found Knative has actually nothing to, we have to implement both the orchestration and many other things from scratch. It's very annoying. But until recently, I found that you have some Air Force flow support for workflow, but this is very great. Thanks for your contribution, and for future project, I think we may possibly switch to your platform. So that's all about my today's talk, and thank you for listening. Okay.
Thank you, Xingda. This is very interesting, and also thank you for sharing your views on the project. Yeah, Airflow is actually a very recent addition. Yeah, we just had a tutorial in SOSP. So Zhuyang here is the one who developed the port. So yeah, it's not super optimized, right? But actually, it's a good workable baseline, so you can play with it, like we are also working on. Yeah, and also we try to open source things, like the baseline things, even before we publish stuff, so that we can give a good platform for people to start using it immediately, so that we build a stronger community. Yeah, so this is kind of the strategy. One question I had, so you mentioned this that you made mitosis work with micro VM. So we actually try to implement taking snapshot on one machine and then resuming a micro VM on another machine based on this snapshot, and we still have the code that is, there are some issues with it. So and the issues are usually, so they seem to be related to the image, actually, to the disk image rather than the snapshot itself. So I wonder if you guys had any problem with particularly this kind of remote snapshot restore when it's taken on a different machine and restored on a different machine.
So your question is what problems we met if doing when we trying to implement this kind of remote fork to micro virtual VM.
Mm-hmm.
So basically, I think the key let me see. First implementing this on micro VM is very similar to container, because from the operating system's perspective, they are both processors. But the key difference, as I have mentioned before, is that the page fault in micro VM is much costly than a container, because you need to first end the hypervisor, and the hypervisor will execute all the stuffs. So basically, one problem we find is that if we use a naive prefetcher, like in mitosis, we only use some temporary locality to fetch adjacent pages. So in mitosis, it works extremely well. But in the micro VM setup, this does not work well, except that we prefetch a lot of pages, but it is very costly. So, but this problem, I think we have currently solved, because we used your approach. Like we can first profile the working set of the running micro VM, and we can use it to price this prefetch. So this can be bring up performance and memory cost, better memory and performance cost. And so one of my students, maybe he is also here. And he found that this is actually very good and very close to the optimal performance, which means that when there's no when we do not use a remote start to run the functions. Yeah. So in others, maybe I think in my opinion, when you bring such kind of checkpoint and restore techniques to a real production, I think there's also still many challenges to address. Because for example, for many kernel state like TCP/IP connections, so how to restore a checkpoint and restore it efficiently. So even I know checkpoint and restore CRU has some support for TCP/IP, but how about some other networking capabilities like RDMA? So there are some research proposals, but I found there's no mature solutions in the literature. And also, I found one important stuff, and I'm currently working on is that how to checkpoint and restore a container that involves GPU. But you know that CUDA actually is very open, closed source, so you cannot do it very by checkpointing state. It's you do not know how to do it. Media does not talk about it. So AMD actually proposed some checkpoints as restore solution, but there's no general solutions for this kind of GPU and XPU. And so I'm also working on this kind of problem, like bringing mitosis to some GPU XPU settings. Yeah,
we are actually also working on GPU called starts for large models. So yeah, with Edinburgh folks. Yeah, so this is really exciting. I think we might be open sourcing something once we submit it. So stay tuned. Yeah.
Looking forward to your work.
But we also noticed that we kind of need to revisit the abstractions. Yeah, because container for GPUs it makes even less sense than for CPUs, because it's kind of a CPU thing, right? So you only attach it because you need something to manage GPU. So yeah, there are some differences there. So what I was also wondering when using mitosis, so mitosis is essentially about virtual memory, right? But technically, when you actually fork the code, you also need to bring the image itself, right? So we had problems with this bringing image part, like devmapper particularly. So I wonder if for example, somebody who did it before could talk to us, or maybe upstream the code that you guys have for mitosis and the micro VM. This would be really, really useful, because we wanted to take a look at like this snapshot storage, or the way how to populate basically how to reissue these forks, right? Like where to store this state, how to account for it. So this is, I think, in production people are not there yet either, in a sense of like, okay, there is a process somewhere, but how do you know where is this somewhere? And so the virtual memory is one thing, but there are also other things that you mentioned, like even without RDMA. Yeah, as simple, we actually had a problem with the disk image, it seems, with XT4 related form problems.
Okay. Yes. I think Professor, your problem is that so different image can only work on some limited platform, right? It's like the 86 image can only work on cannot work on ARM machine. Is that your problem? Yeah.
Imagine we have a Python hello world, and then we take a snapshot, migrate it to a different node, put it in C groups, put it in network namespace, restore a micro VM, and then this Python server just dies inside the guest for no good reason, and we see some ext4 problems. I don't know if you guys face something like this, or maybe there is like someone who is like a guru in this, who is an expert in this kind of stuff. So maybe we can contact them offline.
Yeah, actually, I have thought about these questions before. So for first question, you mean the ext4 file system incompatibility, right? Is that your
We
question?
don't even know, because it happens in the guest, like, and technically everything should be there, but maybe there is something wrong during the migration that happened. But yeah, we basically ran out of time for the intern, or George, he's here, to actually finish the debugging of this part. Technically should work, but there are some issues with the guest, I guess. Maybe George.
Yeah, and it seems like that, like just using some debugging inside the micro VM, it seems as if like the disk state using some utilities like disk. I don't know. I don't remember the utility name. I think it's like disk check X4 or something like that. Like I observed that disk state was okay, and then like I send the request to the container inside the VM, and immediately after that the disk state gets corrupted, as if like the pages were, I don't know, tried to get fetched, and after that the disk state gets corrupted for no good reason.
Probably we wouldn't, figure it out right now, but maybe, I don't know, maybe if you can connect someone to us, then we can discuss in more detail what's happening, like show you the logs. We also try to show it to Firecracker team. So, but their hypervisor part is all good. So the problem is on Firecracker containerd somehow, the way it prepares snapshot.
Yeah, and their agent, it seems something like that, or in the C group part. That's above the, because we also try to just, run a binary inside the container without like containerizing it, and everything worked okay. So like the problem is in the layer between like the fire,
so
the VM and the
yeah,
container.
How will contact the Firecracker team? Since I think maybe they will have some comments about this issue here.
Yeah, we did contact so hypervisor team is like we found that the hypervisor, there's no problem with hypervisor, because if we prepare the guest file system ourselves, the rootfs ourselves, then everything works, right? But the moment we do it with Firecracker containerd, we choose dev mapper, then it doesn't. And Firecracker containerd team is not responsive, unfortunately, even for hypervisor people.
Okay, so it seems something happened in the device mapper, right?
Yeah, so maybe you guys don't use device mapper, or like how what do you do about like disk and mitosis actually?
Yes,
So
actually,
it's still necessary, right?
yeah, we currently use a simple design that we do not use containerd, because actually it's quite slow to start up. So we actually re-implement SOX SOX container runtime to this. So maybe we do not meet such a problem. Yeah.
Okay, but how do you like? What happens if there is any access to disk on the remote guest? Then how do you handle like a disk I/O?
Okay, this is a great question. Actually, currently, you have a disk I/O. We will trap it, and will so first of all, we does not meet many disk I/Os during the most workloads. So actually this we just adopt a very simple design. So if we have a disk access, we will send an RPC to the remote server to read it and read it back. But there, I know there's many corner cases that we have not processed. But I have thought about these questions for some time. So in my opinion, so if you have a serverless computing and you have like some remote fork, like we have some images, we can start from some images. So I think a good paradigm is we can use some distributed file system that we does not use local file system at all, because if your container can start at any place, it is actually, I think, is not very straightforward to like each container will have a local file system. So that's my thoughts about this question. Yeah, and we have not implemented this very well.
I think this is very good question. I think so the problem is that I totally agree with you that there is not much I/O happening. That's for sure. So there's no much point in optimizing it. But for like issues like tail latency, for correctness, probably things may go bad in that case. So I agree that NFS could be a good option, but the problem with NFS, DFS, is that probably you would need a way to establish connection to it quickly. And like the moment you need to do it, probably your kind of migration latency would shoot up immediately just to kind of establish this. Yeah, but this is an excellent question. I think really we should just contribute, contribute what you have somehow. So or maybe like we can take a look at how to migrate this solution to our stack. Yeah, like we are not married to containerd, So if there are some ideas, we always welcome contributions. Yeah. And I think another comment on this slide is yeah, Beehive has many things, right? So there's also, for example, the benchmarking suite, right, which we keep expanding. So currently we just Dockerized, and it can be easily modified to be running kind of in micro VMs, right? So yeah, you can also take a look there. And right now we're adding edge workloads as well. Some of it is kind of embedded GPU ML models, and some cloud gaming, something else. So there are going to be more additions there because we want to also extend it to a cloud edge setup. Have you guys worked on like any cloud edge related stuff?
So currently I'm not working on this kind of stuff. So maybe don't have you work on these kind of areas?
Yeah, and actually not so much, but I think this is a very good case, since the idea of serverless is that we do not need to specify the physical machine that an application will run, right? So basically the service platform can be built based on servers and also on some agent machines. Yeah. So I think it's very makes sense. So but currently I think we have some like related project which is about an operating system named Open Harmony, and yeah, maybe you and
Yeah, I know
and
because this is how I met Xingda actually. So there was a big keynote by Haibo.
yeah, great,
workshop.
yeah.
This is super cool.
Yeah, this project is led by Haibo. So I think we can, like in the edge or in the mobile side, and we will have some like small and based on Open Harmony to support serverless, and we can have other options in the server side. And maybe the key problem will be how can we establish as maybe which will be elastic platform based on the edge, the mobile, and the server. Yeah, but I think it's still for me it's still an early stage project. Yeah.
Same here. So currently we are looking more on like execution patterns, characterization of workloads, rather than the system stack. So we're not there yet, but we already have this cloud edge platform working based on Alibaba OpenYurt.
Yeah, great. Yeah, yeah, and as far as I know, there will be many like available device in the car. Yeah, maybe you will know in the car. So when the owners of the car do not use this device, we can use this device to like support some functions to run. This will be very similar like spot instance, right? In the cloud. But this is I think something like moving computation. Yeah.
Yeah, correct. No, we are also thinking about that environment. So we are more thinking of I mean, cars is one type of devices. There are also a support infrastructure where there like edge servers or along the highway, which somehow need to form these federations of clusters that need to be aware of each other and so on. Yeah, for example, another question is like, how do you do NFS with remote forks and this kind of flaky infrastructure that is kind of come and go all the time? That was also an interesting question, actually, because you lose connections, like you connect to random servers all the time, like there's no state around, like, yeah, what do you do?
Mhm.
I think it's quite interesting, actually. Yeah. And yeah, you also mentioned the serverless bench, right? So this is all very useful benchmarks.
Yes, thanks. Yeah,
Yeah.
thank you. Yeah.
Yeah, I feel like it would be good to form, more of a consortium on this benchmarking part, because probably there are a lot of people using yours, quite a few people using ours. Maybe we can like combine the efforts so that we maintain it together and move forward together. Yeah.
Yeah,
Sure,
I totally agree. As far as I can see, there are many following benchmarks, like Funks Bench, Just Bench, and we have and many others. But for example, for researcher, maybe if he want to make some research work based on serverless, he want to choose one benchmark suite, right?
Mhm.
And to evaluate his system. But maybe currently he needs to consider different benchmark suits and see which one is the best fit. Yeah.
Right. And if
So-
we put, one big one, then people have no choice. They would, make both of us famous, right? So
Yeah.
that's
Diversity
a good
also
thing
matters.
about it,
Yeah.
right?
Yeah.
So that's why I think it's a good idea, and we can always put some undergraduate students, for example, to just work on the benchmarks and package them, and like I think what we achieved is like a very sustainable infrastructure with low maintenance, which just
Mhm.
works for years. So
Okay. Yeah.
continuous
Great.
integration and things like that. So things that are there, they just work.
Mhm. Yeah. And my team also is also working on search bench too. Yeah, we're trying to reorganize some like scripts and test cases. So trying to make it more easier
Mhm.
for people to use. Yeah.
We can also, I'm sure, so iPads is very visible. We also have connections to the industry. So we actually want to form more of like, spec score, something like, okay, this is what providers should compare each other on, right? Like
Yeah.
benchmarks that they would come up with, saying like, look, on these benchmarks, we are better than like Alibaba or better than Google or something like this, right? This is what MLPerf did for for GPU manufacturers, right? And I think they all started in academia, and then eventually it became a standard. We also we are going to I can also show you the dashboard we created for was for benchmarking of commercial providers. So let me share. So we wanted to benchmark providers in the scenarios, different scenarios. So that they can compare, for example, cold starts. Yeah, so there's dashboard where we continuously benchmarking, like generate load and steer it to different providers, and then we can compare. So we have, for example, warm starts, and we have different providers. So you can see what are the warm starts, daily latency, median latency for different providers. We run it every day. So for example, we could get some interesting things where clearly AWS rolled out some change, which decreased the latency substantially. So at least twice. Yeah, which is kind of cool. And code invocations, we also have this benchmarking. So you can compare all the providers. And we also want to add more of image size, like sensitivity, language runtime, some traffic specific, something. So this is already open source. And this dashboard, we're going to advertise it soon.
Yeah, it's very fancy, yeah. And but actually I have one question, since we have also trying to do the same things, but one issue is that for some one issue is that how do we choose metrics, since different cloud vendors maybe will have some their own features in their search platform. For example, the cold start issues, I think is a common case, right, for different vendors. But for example, the function chain or the DAG, which may be implemented by different ways in different cloud vendors. So how do you like evaluate the performance or the yeah of this different like design choice?
Yeah, this is an excellent question. So for vSwarm, we actually have a couple of benchmarks that we ported to AWS and Knative. So technically it can run on Cloud Run and also AWS. But I agree this is very, very difficult to like port every benchmark to run like, on different platforms. So what we did in one of the papers we published in 2021 in it's called Stellar. So this is what the beginning of this project. We just came up with this different, scenarios where we revealed what are the factors that affect cold starts, for example, such as image size, for example. And there are some other things like concurrency of cold starts, how many of them happen at the same time. I think you did similar before, for example, for chains in serverless bench paper, right? So these micro benchmarks are relatively easy to port across different providers. So again, what we are doing is like we are involving like students who would just work on this continuous benchmarking tool, and then we run them every day.
Cool. Yeah, it's very cool.
Yeah. So this is up. We can share this with you guys. This should go live like in December. That's the plan. Yeah, we'll add more of like this and this, and we'll plan to add more like in the next following months. But essentially, the idea is to kind of make providers, showcase their performance with things like this.
Yeah, so I think this will be like become something like ranking, right?
Yeah,
so people
exactly.
will know which platform is like better in case of startup latency.
Absolutely, yeah, exactly, yeah, because they are extremely different. Like just look at this, like Azure 5 seconds, right? Google less than a second. Amazon, actually, when we benchmarked it the first time, it is Python, right? It was like 500 milliseconds. 2 years after, already 200. Like Cloudflare is Wasm style, right? So it's 70 millisecond cold start. Yeah, it's totally different world. Yeah. So very interesting, and you can also see when they roll out optimizations, for example.
Yeah, it's very cool.
Yeah, definitely. We can follow up on this. Yeah. Actually, can I ask a question on Wasm front? So you guys said Xingda mentioned that you worked on Wasm quite a bit. So for example, PyTorch, what was the challenges in compatibility?
So actually, we found there's no fundamental changes. So basically, we have to compile the torch code, the dependency code, to the Wasm Wasm's target, but it is not currently supported by PyTorch native. So we have to do it manually. So this so I think this is some engineering challenge, not some research questions. So we have to pay many. Our students have recompile many modules so as to make it work. So this is the challenges we met. So we actually does not use Wasm after we have failed to do some compilation, right? Yes.
So you actually had to modify the code basically.
Maybe not the code. I'm not sure what code to modify, but we have to modify the build system. and we had to integrate it with existing WSM runtime. So this all takes time. And another challenge, sorry, I forgot to mention, is that current WSM runtime, WSTime, does not have a full support for POSIX system calls. So I've had some missing system calls. So maybe we also need to add this to the runtime. Yeah.
I see. Okay, that's very interesting. Yeah, I feel like you had one more slide actually. So yeah, before I show the dashboard, maybe you can take a look. The outlook or something like this. Yeah, do you still have anything to share?
So I have nothing to share. Thank you.
Yeah, so this is a very interesting discussion. Is anyone any questions? Any maybe do you have any I don't know, requests for Beehive, or what you would like to see, or kind of what would facilitate your adoption, for example, for your project?
So I haven't not tried Airflow yet, but my students have made some look at it. I think it's really amazing. But here's just a trying. So maybe he has some questions. We can use some community tools to communicate. So I actually has a question, not very related to Beehive, but I want to see what's your opinion. So.
Sure.
Basically, I see serverless. How do you see the adoption of a serverless system like Beehive to production? So as far as I can see, that most serverless providers are cloud providers, and they have their own infrastructure to support like serverless. So we can see there are many open source like serverless system, great systems like Beehive, like OpenWhiskey, but to the best of my knowledge, I have seen very few production company to adopt so because company do have their own solutions. How do you view this kind of thing?
This is a very good question. So we never position it as like an alternative for people to adopt it in production, or we do a startup or something. But there are some really good indications happening right now. So Beehive is like, there are two main technologies that it adopts: is Firecracker, which is production technology, right, and Knative, which is actually something under Google Cloud Run. So from that perspective, you can already say, like, look, Red Hat, and which Red Hat is owned by IBM, and Google, which also are, like, they are not the biggest, but they kind of run this stuff. So it's kind of the one that is representative already. Obviously, there are some configuration issues and things like that. Then other open source technologies. So when it comes to OpenWhisk, as far as I understand, there haven't been commits to OpenWhisk for like years already. So it's kind of abandoned, except for researchers who still, do research with it. So in retrospect, it's good that we didn't decide towards OpenWhisk at the time when we made the decision. Other solutions like OpenFaaS and things like that, we haven't adopted them at the time because they had more automations than we wanted. Knative actually had the least amount of automation, so you just have YAML files and you go with them. So that was the reason why we adopted it. And I think the choice was right, because this is what the company also started to adopt. But yeah, we still, like, Alibaba would probably use their stack, like Amazon uses their stack. So that's a long term. We'll see, right? It's like Windows against Linux race, I would say. But we are not Linux yet. So that's the difference. Another thing is I recently seen the paper in SOCC by your group. I think Dudong, you were there. I think it's the gap between the research systems and the real world. And I was glad that you guys used one of the Kubernetes-based platforms. I think it was Knative, right? Or OpenFaaS. I think Knative, right?
Yeah, Knative and Open. Yeah.
So it kind of, if it makes sense for people in the industry, it seems it makes sense, right? I also am in touch with Amazon, right? So when I'm telling them, like, look, your control plane is too heavy, they're like, yeah, we know, right? So we can just, our community is big enough, your community is big enough, so we can just make a choice and go with Knative, for example, as opposed to like shooting in all different directions with OpenFast, OpenWhisk. Like OpenWhisk would be just the wrong choice if somebody's choosing a platform today. I think all others are possible.
Yeah, I agree, and that's also why we want to write this paper, because we do see some like gap between the research work and the industry, and the fact is that we think that the service stack in the real world is not perfect, or maybe or it's far away from ideal, right? And there are still many remaining issues, like how to design the infrastructure for servers. Actually I do not think Kubernetes is the final choice. Yeah, it has many issues like declarative text and many other issues. Yeah, and the control plane is very heavy compared with the lightweight service functions. So yeah, I do agree with you that we still have many things that we can do for research, and maybe some ideas can be adopted by the industry, or more ideally, maybe our system can be adopted by the industry, right? So the open source community, yeah.
Correct. I think where we have real handle is we can push the research community to use this as a standard ecosystem. So people compare not OpenWhisk to OpenFast to like something else, right? Because this is what happens in the community right now. Like everybody picks their own traces and their own baselines, and then they try to mimic each other. But this is not a very productive way for the community to go forward. So one of also the latest editions that we add in SOSP, we published the standard traces sampled from Azure production traces for a different function count. It's called in vitro, and it does support 3. So this is a load generator for kind of scale down traces, which are kept representative with our sampling methodology. It supports Knative, it supports OpenWhisk, it supports AWS right now. So you can, for example, steer the traffic on your cluster and see what happens, and like somebody else will take the same exact 100 functions, randomly selected and the most representative ones, right, and steer it on their cluster, and then we can compare, right?
Yeah,
so,
it's very valuable.
Yeah. So
Thanks,
you guys can take a look, like take it for the test drive. We have quite a few groups working with it right now. So on very different aspects, like for example, this is like let's say Azure production traces, or maybe somebody who prefers like Huawei traces that are recently published.
Yeah.
It's easy to adopt them, and then you can use it for functions. You can use it for GPU as a service, like for AI or for something else, because they all have similar requirements. Bursty traffic, like very careful, accurate measurements. That's what the platform does. So yeah, any other things that?
Yeah, maybe I have some little questions. So yeah, I'm also from SJTU. I just graduated there, so I've heard of iPad's name for multiple times. Yeah, and about the paper, I think you implemented about the MTOS, or yeah, about that paper. I think you implemented a really fancy like distributed memory paging system on the CPU. So I'm wondering, is there like, are you heading towards like are heading towards a more fine-grained like GPU distributed GPU memory managing system? Because as far as to my knowledge, the current GPU memory managing system is really very naive. So do you think there is such like opportunities for like a more fine-grained distributed memory managing system on GPU or on like other hardware resources? Yeah.
Oh, this is a very good question. And but as far as I know, do you know the NVIDIA has released a cluster a super machine called Grace Hopper?
Yeah.
It kind of like implement in my opinion, it kind of implement the distributed GPU memory management you mentioned, because it support up to 256 nodes that connected into a coherent distributed space. I think this is very wonderful, and they implement the paging like what from both NVLink and the OS, and you can application can transparently run your application on this. I think NVIDIA has quite do such kind of stuff.
I see.
Yeah, this is actually great you mentioned. I remember at SOSP there was a paper that was doing some GPU memory management for recommender systems from, I think also from your group.
Yeah, that's one paper. The paper doing so manually, so you have to use some planning to do the caching. But what I mentioned is that the NVIDIA has do it in the hardware. So this is very cool. But I think there's definitely research opportunities, because hardware distributed shared memory is never successful. So as far as I know,
That's true.
Yeah, so I'm a big fan of distributed shared memory, but I know it's not successful now. So Grace Hopper, as far as I know, they turn off the cache coherence by default, because we know cache coherence is slow. And I think with the hardware, we can maybe like some co-design to make it more efficient to manage GPU memory. This is really great place to work.
This is super interesting. We're also kind of looking at I/O and memory management for large models and like GPU clusters and this kind of stuff. I guess the question is like how easy it is to get your hands on, Grace Hopper in reality or something similar. What are you guys thinking about it?
So for you guys, I think you can buy the Grace Hopper machine, but we are at China, so we actually cannot do such stuff. So we currently cannot do things on this. We even cannot buy A100.
Yeah, I heard about it. Yeah, but actually, if we are able to get to a Grace Hopper, I started talking to NVIDIA a bit, but it didn't go that far yet. And I don't think other vendors like AMD have any alternative to it. But if we get our hands on Grace Hopper, maybe we can also see if it's possible to somehow do experiments on it together, for example, right?
Very cool. Thank you.
Yeah, for sure. Also, like there are many opportunities to work kind of collaboratively between Singapore and China. For example, this CSC program, where PhD exchanges. So we actually host a student from Nanjing University right now, Hancheng.
Yeah, we have many students from Nanjing University.
So we can, for example, if we have like a Grace Hopper, I don't know what the like ways to work on it together, right? But this could be definitely an opportunity if you guys have like 1 million students, right? You can just send some here, to do the work, right? So I'm sure there might be a way to constructively work on it, on these interesting topics. And I briefly talked with Haibo, so if I come to Shanghai, maybe we can arrange also a talk from our side. Have another.
That would be great.
Also, feel free to join the Beehive community meeting. So we are trying to attract speakers, and we're trying to expand the community. So we get more attraction because for example, Sisa Mao, Stanford YouTube channel, you probably heard of it, right? So that's kind of the role model where we kind of trying to push it eventually. So also, for example, if you know good speakers, interesting work, some principal engineers or something, then we can also invite them to give a talk. Currently, it's once in 2 months, but we'll look to increase the frequency to monthly eventually.
No problem.
All right, excellent. So great to see you guys. So we'll process the video and we'll post it on YouTube if nobody minds.
Okay.
Great. Thank you so much. It's been a wonderful discussion. Say hi to Haibo and the folks.
Okay, so yes. Thank you. See
Pleasure
you.
to
Yeah.
see you like
Yeah. Bye.
face to face. Bye bye.
Thanks, bye.
Thanks.
Bye
Bye.
bye. Bye. Thank you.
Thank you,
See
Xingda.
you.
Appreciate it.
Thank you. See you in